Okay, this is lesson 1 for chapter 17. This is our last chapter, and this chapter is on acids and bases, so we're just going to do a brief introduction here. There's a worksheet that goes along with that. You should have seen that posted this morning. Again, if you have any trouble with any of this, I'll be holding office hours tomorrow, and you can pop on there and ask any questions you might have. Alright, so we're going to look at chemical and physical properties of acids and bases. We're going to look at the solutions and how they're classified as acid, basic, or neutral, and then we're going to look at the 3 models of acid-base theory. So there's a lot of vocabulary here. There's probably a lot of new vocabulary in here. Hopefully we'll answer all those as we go through. Most of this vocabulary is going to center around the 3 theories, which are the Arrhenius model, the Bronsted-Lowry model, and the Lewis model of acids and bases. Remember that a Lewis structure is a dot diagram showing the number of valence electrons around an atom. You can have a Lewis structure of a molecule, like you could have a Lewis structure of water, which would be an oxygen, and we usually do it in this kind of formation to show its bent structure, but that's a Lewis structure. So just kind of remember that, because that'll show up here in a little bit. Alright, properties of acids and bases. You'll see this on tests. You'll see this on the chapter 17 test for sure. What are the properties of acids and bases? You come in contact with a lot of acids and bases. Vinegar is an acidic thing that you come in contact with. Lemon juice, you've probably seen that or used that in cooking or baking. Those are both acidic solutions. Soap and baking soda and bleach are all basic. Okay, so those are basic solutions. Well, baking soda when it's in water, or soap in water, not as the dry compound. The physical properties of acids and bases. Acids taste sour. So if you've ever tasted anything that was sour, it's an acid automatically. Bitter, it's hard to say what actually tastes bitter. We don't really taste a lot of bitter things. Soap, if you ever get soap in your mouth while showering, or you put your hands in your mouth while you were dealing with soap, you'll notice it has a very distinct bitter taste. Texture, when you have a solution of acids and you rub your fingers together, it kind of has that squeaky clean kind of feeling, where the skin does not slide past each other very easily, whereas bases are slippery. If you stick your fingers in a basic solution and then rub your fingers together, it's slippery, like you've got soap on your hands. Conductivity, they both conduct electricity in water, and that's because they're made up of ions. So acids and bases are made up of ions, and we're going to talk specifically about those ions here in just a second, but because there's ions in water, it conducts electricity. There's a couple of reactions that you need to be familiar with. They are mostly revolving around acids. There's more than just these, and if you take IB Chemistry junior senior year, you'll learn a few more, but for the most part, these are the 3 common or most common reactions. So neutralization is when an acid and a base react together and they produce a salt, and so the salt is not table salt, but rather a salt. So it's whatever the acid and base are. So the salt is actually the cation from the acid and the anion from the base. They go together to make salt. In this case, we use sodium hydroxide and hydrochloric acid. It formed sodium chloride as the salt and water. So all acid-base reactions will produce a salt and water. An acid-metal reaction, not all metals react with acids, but most do. We say that if they react with an acid, we call them an active metal. And so an active metal and an acid will always produce a salt and hydrogen gas. You've seen this one right here, this reaction in the lab whenever I make hydrogen gas. That's magnesium put into hydrochloric acid, and it forms magnesium chloride solution and hydrogen gas. These are all salt solutions being formed. I didn't put the states in there. And then the last one is an acid carbonate. You've seen this if you've ever done a baking soda volcano, or if you've ever seen anything react with acid that produce like a lot of bubbling, your Alka-Seltzers and things like that. A lot of those are acid carbonate reactions. So this one again is hydrochloric acid plus sodium carbonate, and they will always yield a salt, water, and carbon dioxide. And of course that carbon dioxide is released as gas, and that's the bubbling you see. So those are the three common reactions with acids. There's more than those, but we're only really going to hit those three. All right, so let's talk about the ions that are found in acids and bases. Water, I'm just going to move over here real quick. Water by itself will actually what we call self-ionize into hydroxide and H+. Okay, now this H+ is not pure H+. It's actually two waters are going to interact together to make one hydroxide plus, and that hydroxide's got a negative charge, plus an H3O+. This we know as hydroxide. We learned that in our common polyatomic ions. This guy is called hydronium. And so those are the two ions. They are found in all samples of pure water. If it's pure water, then it's going to have equal numbers of hydroniums and hydroxides. Now, very few, tiny amounts of it. The vast majority of water in pure water is H2O. So this guy right here is the majority. That's the majority of the water in a sample. These guys here are a very small fraction, so small amount. And when we say small amount, we're going to say very small amount. Okay, so those are the two ions, and that's why acids and bases conduct electricity. Neutral water doesn't conduct electricity because there's just not enough hydroniums and hydroxides. So if it's got the same number of hydroniums and hydroxides in the solution, we're going to say the solution is neutral, like normal water. However, if the solution has more hydronium than hydroxide, we're going to say that it's acidic. So it's going to be in this category here. Now this is showing H+. H+ and H3O+ are the same thing. Those are two different ways to write the same thing. So if you see H+, you could call it hydronium. If you see H3O+, you can call it hydronium. So it's the same thing. It just gets annoying writing H3O+ all the time. So we just say OH- and H+. If a solution has more hydroxide than hydronium, then that is going to be considered to be basic. So over here we have hydroxide here. It has more hydroxide than hydronium, so we're going to say that it's basic. So really, acids and bases, or acidic and basic solution, is just how much hydronium and how much hydroxide something has. If it has the same amount right in the middle, it's neutral. If it's got more hydronium, then it's acidic. If it has more hydroxide, it's basic. So there's three models that we have historically used to talk about acids and bases. The oldest model is the Arrhenius model, and it just states that an acid is a substance that contains hydrogen and ionizes to produce hydrogen ions in aqueous solution. Now that's a kind of a long drawn out definition, but basically Arrhenius said that if this thing produces H+ in solution, it's an acid. So anything, if you put it in water, if it increases the concentration of H+, it's an acid. Whereas a base is anything that increases the concentration of OH-. So if you have sodium hydroxide and you put it in water, the amount of hydroxide goes through the roof, which means it's increasing in concentration, therefore it's a base. So anything added to water that increases the concentration of hydroxide would be a base. So that's the Arrhenius definition. It's circled or focused mainly on putting something in water. If you put something in water and all of a sudden there's more H+, it's an acid. If you put something in water and all of a sudden there's more OH-, it's a base. All right, the Bronsted-Lowry definition. In the Bronsted-Lowry definition of acids and bases, it's all about what happens in a chemical reaction. Basically, an acid is something that gives up a proton. That's the H+. If you figure hydrogen is 1 proton and 1 electron, H+ is 1 proton and 0 electrons. So essentially, it's just a proton. So when we're talking about H+, we're talking about protons. So Bronsted-Lowry definition just said an acid is something that donates a proton in a reaction. So if we look here, we have HF. That's my acid because it's got a proton. And at the end of the reaction, it has donated, it gave its hydrogen over, or its proton over to the water to make the water H3O+. So consequently, I have a donation of a proton. Now we can look at this using a reaction we've already looked at, HCl plus NaOH, and that's going to yield NaCl plus H2O. Well, if we look at this, the proton from the HCl gets donated to the OH minus, and they together make that water. So this guy, this HCl, donated a proton. It gave it up. That makes it an acid. Well, in the Bronsted-Lowry definition, a base is a proton or a hydrogen ion acceptor. So if we go back to our reaction here, we see that the H+, this is my H+, which is basically just a proton, is being donated from the HCl, which makes this the acid. And the NaOH is accepting that proton, which makes it the base. And so when it accepts the proton, we have water forming, and then the sodium and the chlorine join together to make the salt. So that's a Bronsted-Lowry definition of an acid and a base. It's pretty easy with Bronsted-Lowry. If I gave you this guy and I asked if that's an acid or a base, you're going to say, well, it's got H's in it, which means most likely it'll be H+, donor. It's going to donate a proton, which means that's an acid. If I gave you something like MgOH2, you're going to say, well, that's got hydroxides in it, so more than likely it's going to be a proton acceptor to make water, and so therefore you have something like a base. So that's what we would say. So the Bronsted-Lowry definition is all what happens in chemical reactions. However, the Bronsted-Lowry definition can take something like NH3 plus H2O, and when NH3 and H2O react, this is ammonia and water, you end up forming NH4 plus OH minus. Okay, so in this one, it's kind of hard to see without looking at the whole equation who the acid and base is. If we look closely, we see that the water actually donates a hydrogen, an H+, to the ammonia. And so that makes water, in this case, the Bronsted-Lowry acid, and ammonia the base, because it accepted the proton. And H+ was transferred, which is basically just a proton. All right, so that's the Bronsted-Lowry definition of acids and bases. Now, another aspect of the Bronsted-Lowry definition is the idea of conjugate acid-base pairs. So this is, you just have to follow it a little bit. It's pretty easy to see once you know what you're looking at here. So a conjugate acid is the species that's formed after the base accepts a proton. That's the conjugate acid. So let's look at this. If NH3 is the base, that's this guy. If he's the base, he's accepted a proton from the water. So an H+ was transferred. That makes water the acid and ammonia the base. What this guy becomes when he accepts the proton as the base is the conjugate acid. So we just say it's the conjugate acid because now it has one more proton than it did. The conjugate base, on the other hand, is the species that is formed after the acid donates its proton. So the water is the acid, it donated its proton, so it became the conjugate base. Now this is only really important in reactions that are reversible. See this little double arrow right here? That's showing that the reaction can go forward or backwards. So in the forward reaction, ammonia is the base and water is the acid, but in the reverse reaction, ammonium is the acid and hydroxide here is the base. So this is ammonium and this is hydroxide. So that's the reverse reaction. So we're just going to say that these guys are paired up, and if you look at them, if you write the base, we call them acid-base pairs, we're going to say the acid is H2O and its conjugate is OH minus, and the acid in the reverse reaction is NH4 plus and its conjugate is NH3. And if you look at this closely, it should be pretty straightforward. If this is the acid and this is its base, its conjugate base. If we look at this, we're going to say this is 1 proton less. This has 2 H's, this only has 1 H. This has 4 H's, this only has 3 H. And so if we look, we can see it's just 1 less both times. All right, so that's the idea of conjugate acid-base pairs. Another idea we have to look at is how many hydrogens there are in a thing. So we can look at them and call them monoprotic or polyprotic acids. So one hydrogen's mono, mono, poly, more than one, mono, mono, mono. Okay, so when we start looking at these, this is mono, poly, poly, mono, poly, mono. All right, so we have the idea that there's more than one donatable or hydrogen, more than one hydrogen that can be given up. But these are the conjugate bases. On the other side, you can see they're all just minus 1 H. So if you take the original formula and you subtract 1 H, you have the conjugate base. Some things can act as both acids and bases in different situations. The most common of these is water. Water is said to be amphoteric. That's how you pronounce this word, amphoteric. Anything that can act as both an acid and a base is considered amphoteric. So I have two equations here. I have water reacting with hydrofluoric acid or hydrogen fluoride in solution, and that's forming H3O plus and F minus. And so in this case, the H is the HF is donating a proton to the water. So the water is a proton acceptor, which makes it a base. In the second equation here, water is donating a proton to the ammonia, which makes water the acid. So is water an acid or a base? The answer is yes. Sometimes it's an acid and sometimes it's a base. We call those compounds amphoteric. There's more than just water. Water is just the most common. We've already hit this, monoprotic versus polyprotic. If it has two, sometimes we call it diprotic. I'll let you guys read through this, but if it only has one hydrogen that can be donated, it's monoprotic. If it has two, it's diprotic. Typically, if it has three or more, we call it polyprotic, but technically, diprotic acids are also polyprotic because there's more than two. All right, the last model we're going to talk about is the Lewis model. If you guys remember Lewis structures, it was all about electrons, and so the Lewis model is all about electrons. The Lewis model doesn't focus on hydrogens, it doesn't focus on hydroxides. What it focuses on is electron pairs. So it says anything that donates a pair of electrons is a base. So a Lewis base is an electron pair donor. Therefore, a Lewis acid is an electron pair acceptor. So in a reaction, if something accepts an electron pair, it's an acid. If it donates an electron pair, it's a base. And so here's two reactions right here. This one we have fluoride reacting with H plus to form hydrogen fluoride. And so H plus has no electron pairs, so that H plus is going to bond to this pair of electrons right here. Well, because because of F is donating the electron pair, that makes it the base. And because hydrogen is accepting the electron pair, that makes it the acid. So it's all just what's happening with the electrons. Here's another example. We have oxygen ion is going to react with sulfur trioxide, and this sulfur trioxide is missing a pair of electrons here. It doesn't have a pair, and so this pair of electrons right here is going to bond the oxygen to it, And so in that case, oxygen is going to be the base because it's the electron pair donor. So that's the pair that will be donated. And that makes it the base. Therefore, the sulfur trioxide becomes the acid. Now, because this isn't dealing with only hydrogen and hydroxide, it makes the definition very large. So a lot of times you'll see a drawing like this, and then like this, and then like this, and we will say that this is Lewis, and this is Bronsted-Lowry, and this is Arrhenius. Basically, an Arrhenius acid and base is also a Bronsted-Lowry acid and base, which is also a Lewis acid and base. But there's some things that are Lewis acids and bases that are not categorized or cannot be classified as Bronsted-Lowry or Arrhenius. So the Lewis is the largest definition. As you see, there's no, in this bottom one here, there's no H plus or OH minus, therefore it can't be the Arrhenius definition of acids and bases. It also doesn't have any protons being donated or accepted, therefore it's not a Bronsted-Lowry acid or base, but it is an acid-base reaction based on the Lewis definition. So here's all three. This just kind of breaks it down for you. Sorry about that. You have the Arrhenius, which is an H plus producer or an acid, and an Arrhenius base, which is an OH minus producer. Bronsted-Lowry, proton donor, proton acceptor, and Lewis is going to be an electron pair acceptor and electron pair donor. So hopefully you were able to get through the whole worksheet. There are 2 lessons today, so when you get done with this one, at some point before Wednesday, jump into the next. I hope you guys are doing well.